Apparently, my computer's on the same circuit as the kitchen.
So we're live. So when
Okay.
you turn on a computer, it shuts down the kitchen?
Or more to the point, when they throw the breaker in the kitchen to replace some things in the ceiling, it takes out my computer.
Oh, so people didn't know that you, for example, needed a computer, and so they were throwing the
They
breaker in the
didn't know
kitchen.
there's so the kitchen is on the other side of this building. There is no reason for the outlets I'm plugged into to be attached to the kitchen,
Yeah.
but wiring.
Mm-hmm.
As we've all learned in our houses, there is sometimes that one outlet that you're
Yeah.
not sure why it's attached to the breaker it's attached to.
I have these cool little USB plugs that I had installed in the house, so you can just plug your USB cable directly into the wall.
Yeah.
Except they all stop functioning after some period of time because some breaker gets kicked. And then when the breaker gets, when for some reason like the power goes out, then they all work again. And then one by one, for some event, we'll take them offline. And then the power goes out in the house, and then they all come back again. So I don't understand. I thought it was so cool that I could just have these little
Hmm.
plugs in the wall that you could plug your
Yeah.
phone into,
Yeah,
and
we have some of those.
yeah, and then they just stop working. So, but they work as regular plugs. So the regular plug part works. So I, I don't know what's going on. Anyway,
I just buy power strips now that have USB ports on them.
yeah, I have the same thing. Costco, I just buy them in bulk and just put them everywhere. I think I'm not kidding. I think I have like 5 of these.
Oh yeah, I
Yeah,
have that many. I was just like, you said Costco, and in my brain, you had a cart that's just like the bulk 100 pack of power strips, and
yeah,
that was a
yeah.
fabulous
No,
mental image
I
to
didn't
have.
buy 100, but I feel like to just go in and throw 5 power strips, 5 power bars into your cart at the same time is, it's that's a serious commitment to having
Yeah.
a lot of power out there.
Yeah, so I do that at Home Depot
Yeah,
periodically, and at Home Depot, it just seems appropriate.
yeah.
I don't know why.
So if you're wondering what it is that you have stumbled into, this is a live episode of Astronomy Cast, and it's going to be a special two-parter. So we're going to be recording episode 541, which will take us about, I don't know, like we'll end sometime uh, in about 30 minutes or so. And then we will shut down this live stream and we will start up a new one and we will continue on with the show. And that is
Yes.
because we need to have sort of 2 separate pieces that Susie can use to promote, and this is because you are going to be on the road for next week. So
Yeah, I am going on vacation with a friend, and we are going to be driving back from Los
yeah,
Angeles. And so wanted to make sure the science kept coming.
yeah,
That seemed like a reasonable goal.
yeah. So I'm going to say hi to Adam Synergy, Andy Cowley, Ben Kalo, Bill Sugden, Catalin Bontia, Chai Latte Nebula, Cherry Cat Naps, Colin Jones, Dustin King, Dusty Reichwin, Frank Tippin, Giselle Sabrin, Gordon Dewis, Graham W., Guido Bibra, Holly Meyer, Janelle Duncan, Jessica Feltz, John Anthony, John Drake, John Richards, Kira H., Quadlibet, Linda Sedik, Nancy Graziano, Orbit Over Luna, Paul Disney, Paul Gracie, Raj Luthra, Sean Kenny, Side MT, Susie Murph, Tom Van Scotter, Tommy Vask, Umu, Wayne Johnson, Yamagashi Sun, and Zapfan Zapman. Hey, everybody. Uh, how's it going? Rich 901, Therion. I think we got y'all. Okay, well, let's get started then, whenever you're ready.
Okay. Sorry, I'm just setting up to be able to answer you when you say, do we have anyone to thank at the end
Yes,
of the episode?
and break it up for 2 episodes.
Yeah. All right. So I think I am set to handle that question. I am moving the Slack over there. So this is what happens when I'm in a new location. I just get slightly confused. But Audacity is not using the right mic. Audacity.
Oh, you cut your audio entirely. So Audacity is going to have to share. Audacity
Can you
wants.
hear me now?
Yep.
Okay. No idea. Audacity does not work and play well with others.
But now is it using the right mic? But you also get to use a mic for doing this show? Okay, great.
Yes.
Right on.
Okay. I'm ready to press record if you are ready to press record.
I have pressed record.
We are recording. Hello, Susie.
Well, Susie, have fun with this one. Astronomy Cast, episode 541, Weird Issues, the expansion rate of the universe. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. I'm actually at the Planetary Science Institute this week,
Yep.
and it has been an amazing adventure, but it also means the audio is going to sound a little bit more hollow today because I got to borrow a friend's corner office, and it is awesome, but a little hollow sounding.
Not as soundproofed as the home office that you normally record in.
No,
Yeah.
It's true.
Yep. So, just when, did I say the wrong intro?
No, you said entirely the right intro.
Did I say Weird Issues, the expansion rate of the universe? I don't think
Yeah.
I did.
Yeah, you did.
Okay. All right. Okay. You have to cut that out, Susie. But just in case I didn't, Astronomy...
Do you want to start over?
Nope.
Okay.
Astronomy Cast, episode 541, Weird Issues, the expansion rate of the universe. Just to be safe. And then, whichever cut sounds better, Susie. Go ahead. Just when the universe was starting to make sense, the cosmos throws a curveball at us. Astronomers have been trying to accurately measure the expansion rate of the universe as far back as Hubble. It's been tough to nail down, and now astronomers are starting to figure out why. All right, Pamela. Why is the expansion rate of the universe important to know?
It's one of those things that really defines what is the likelihood that different blobs of matter are going to have a chance to come together. It is the thing that defined what was the density of material when stars were ready to form. It is the thing that will eventually define, does our universe tear itself apart or collapse back in on itself? So by understanding the expansion rate, along with other factors like the geometry of the universe, which is not a controversy, the mass density of the universe, which we think we have a handle on, the expansion rate is that other thing that helps us define the evolution of our universe.
I mean, you can kind of imagine, I love this idea, whether it was Hubble or some other people were working on this idea as well, where you observe these galaxies in all directions, you detect the redshift, and you realize that in every direction that you're looking, galaxies are moving away from us. And then you immediately realize, you've got to be either everyone is afraid of us, or the entire universe is expanding, and that means that it was once in a smaller location backwards in time and could have a definitive point. So was this a revelation? This must have been a big deal when it all came together.
It was definitely a moment of, what the universe? You're not supposed to act that way.
It all goes it was always and forever, right?
Yeah. So back when these observations were first made by Vesto Slipher, he was the one that really got us into this mess. It was thought that the universe was a steady state creation where the size of the universe was what it is and always had been and always would be. And if you look out at the galaxies, you should see random motions. And it was off of this steady state idea that Albert Einstein stayed the universe in his equations so that it neither contracted nor expanded, but instead just sat there going, I'm a universe. But when Vesto Slipher first looked out and started doing spectroscopy of galaxies and measuring their motions in the sky, we didn't at that point know how to measure distances. But he expected to get a distribution of motions where some are coming towards us, some are going away from us with a variety of different speeds. And what he found is, yeah, there's a few that are coming towards us. Andromeda, we're looking at you. But the majority of the 20 some odd systems that he looked at were moving away. And this was not something that made any sense. And this was data that Hubble took, and with the work of Milton Humason, who did a lot of the observations for Hubble, they combined their redshift determinations, that measure of how fast things are moving away from us, with Henrietta Leavitt's work that allows us to measure distances to things relatively using Cepheid
Right.
pulsating variable stars. And he was able to make that first measurement of this is how far away the galaxies are compared to one another. And this is their motion compared to one another. And the further they are away, the faster they're going.
And so, how do astronomers define this? Like, if you ask an astronomer, how fast is the universe expanding? What is the expansion rate of the universe? How do they describe this expansion rate?
Well, like so many things in the universe, since we can't see the whole darn universe, we don't say the universe is expanding at and give the rate the entire universe is expanding at. We instead break it down into manageable pieces. And in this case, the manageable pieces are still really large. And what we say is the universe, for every megaparsec of space that you have, that megaparsec is getting bigger by the expansion rate every second. And that expansion rate is where we get ourselves into trouble, but its value has generally ranged from 0 to 1,000 kilometers per second, depending on who took the measurements.
Right.
So it's a 60, 70 kilometers per
Okay.
second for every megaparsec of
Okay, so let
space.
me just sort of see if I understand this. So you've got a megaparsec, and that's a
Yes.
gigantic
Oh,
chunk
yeah.
of space, right? A megaparsec
Yeah.
is thousands of hundreds of thousands of light years,
Mega is
millions,
million.
millions of light
So,
years. Yeah, the parsec is
yeah.
like 3 light years, and so, you know,
Yeah.
a lot. And
Yeah.
so every second that, if you're at one side of that, a box that defines a megaparsec, and then someone else is on the other side of that box that defines the megaparsec. 1 second later, you are now roughly 70 kilometers farther away from each other. And then
Yes.
1 second later, you're now 140 kilometers away from each other. A billion years later, your things have really moved.
And it adds up. So if you have 3 megaparsecs between you and your friend, first of all, you're never speaking to them. Second of all, that megaparsecs, it's expanding apart at 270 kilometers per second. And sorry, 210 kilometers per second. If you have 4 megaparsecs, you're now at 280 kilometers per second. And it adds up so that when we're looking out at the furthest edges of our universe, we're seeing things that are trying to accelerate away from us at the speed of light. And
Right.
it's not that they're moving faster than the speed of light, it's that all these different individual megaparsecs are all getting bigger. And it's pushing things out of the way as it does it.
And I'm glad you made that clarification at the beginning where, I said like how fast is the universe really kind of getting bigger. And I think, we imagine if someone is like inflating a balloon or inflating a bubble, you can imagine that bubble just getting bigger and bigger and bigger. And
Yeah.
you could measure, the bubble had a diameter of this number, this second, and then 1 second later, the bubble has a diameter of that second, and those numbers are bigger. But if the universe is infinite, you can't say that it is getting bigger because it's forever before and it's still forever. And even if
Right.
the universe is finite, we don't know how big that finite is. So it just doesn't make any sense to say, here's how big this ball that you're imagining in your mind, and I know you all are, that you can't rely on that. And so that's why astronomers just go, let's just measure the things that we can measure, which is smaller chunks of the universe.
And this is what we do. And because we can see things multiple megaparsecs away, we're able to systematically say, yes, we see this change. Now, where it gets trickstery is while we have the ability to see several megaparsecs away, we aren't always so good at measuring exactly how many megaparsecs things are away. And this has caused no end of difficulty across the decades.
Right. And so you go back to Hubble's original measurement, the Hubble constant, which really defines this. And what's this? We're closing in on 100 years since Hubble made
Yeah.
these measurements, and astronomers still argue over what the Hubble constant is today.
Mm-hmm.
And in fact,
And
part of the reason why we're in this weird issues place is because it is something really complicated to try and understand. So can you just explain the challenge and why it's become so complicated?
and it all comes down to trying to measure distances. And space isn't a place where we can just casually go out with our ruler and measure from point A to point B. It's not some place where we can consistently go out and use radar to measure distances. We can get away with that with asteroids and other planets occasionally. But in order to measure the distance to other stars, we really have to use parallax measurements. This is where we wait for the Earth to be on one side of the sun. We measure a star against background galaxies. We wait for the Earth to come around to the other side of the sun. We measure the position of the star against background galaxies. And our motion from one side to the other will cause the star to appear to move relative to those background objects. And this is the kind of thing that you can experience for yourself just by holding your thumb out at arm's length and blinking between two eyes and seeing how your thumb appears to move against background trees, mountains,
Yeah.
whatever.
Or like when you're driving on a car really quickly and the trees are going past you while the mountains aren't.
Exactly.
Yeah.
And this parallax effect requires objects to either be fairly close so you can see this jump, or requires us to have extremely high resolution detectors. Now, Cepheid variable stars, while wonderful in many ways, do not live near the planet Earth. And so we haven't been able to get high quality parallax measurements of them until fairly recently. And it's the debates we have had in trying to figure out the distance to the nearest Cepheid that has led to a lot of the squabbling in our community. Now we have Gaia. Gaia is doing marvelous work. New methods of using the Hubble Space Telescope have been devised, and people are finally starting to get results that we think are accurate within a couple of percent for this first indicator that we use for measuring distances to galaxies. So once we can measure accurately the distance to the nearest Cepheids, that gives us the 0 point of our ruler.
Right. This is a ladder, right? We're building a ruler where the first piece of it is this parallax measurement that allows us to measure the stars out to what? Like the nearest few thousand light years away.
Yeah.
And then it's that amazing relationship with Cepheid variables, how they oscillate tells you their intrinsic brightness, and then you can use that to tell how far away they are. And then that lets you ladder up to now, because you can see Cepheid variables in Andromeda and you can see them in other galaxies far away.
And up until our recent spacecraft measurements, we could always say what was closer and what was further based on apparent brightness. The same way you can look out in a field of lightning bugs and know which lightning bugs are nearby and which are far away based on how bright they appear. Now,
Because
it's
you know how
cool to
bright a
know.
lightning bug is.
Well, you don't even have to know accurately how bright
Right.
lightning bugs are. You just need to know all lightning bugs are giving off basically the same amount of light. And as long as all lightning bugs are giving off the same amount of light, if you see one that's faint, it's far. If you see one that's bright, watch out.
Yeah.
And so we didn't even have to know exactly how bright Cepheids are to know the relative distances to galaxies. And this is where Hubble was able to get his first distance concept of, I know this one is closer, I know this one is farther, but then accurately figuring out exactly how much closer, exactly how much farther. This has been the stuff of legendary battles
Yeah,
in the field of astronomy.
right. But of course, in 1998, with the discovery of dark energy, it turns out the expansion rate of the universe is changing over time. So it's not just that you have to make the most accurate possible measurement. You literally have to then figure out a way to measure distances at
Yeah.
different points in time.
So we went from multiple decades of, is it 50 or is it 100? Because basically two different individuals, Alan Sandage and Gerard de Vaucouleurs, were steadfastly arguing one way or the other, and you had to side with one of them or you were an evildoer. And if you sided with the wrong one, you were still an evildoer. It was very partisan politics as far as the Hubble constant was concerned. And luckily, I had instructors that were like, we don't know, just use 100. It makes the math easier. And then with the Cepheid Key project that took place in the 90s, with Hipparcos data, with increasing accuracy from our spacecraft, we began to really hone in the early 90s to, it looks like it's somewhere between 65 and 75. And then, like you were saying, in 98, it was just like, oh, expletive. As you plot things out farther and farther, that will get you more accuracy if it's a constant, because you can fit the line better if you have a longer line that you're trying to fit. But it wasn't a line. It turned out that it was a slight curve. And as we went out to greater and greater distances with supernovae that were calibrated using the Cepheids, we saw this turn that could only be explained by the universe accelerating itself apart.
So, how much of an impact is this? Like, we are, and of course, our next episode is why it's been so difficult to talk about the
Right.
age of the universe. But here we are, some number of low teens, billions of years into the age of the universe. Is that dark energy having a big impact on the rate that the universe is expanding apart?
It's not a huge impact,
Like in that
but
velocity number?
yeah, it's not a huge impact on the velocity number, but it's enough that it makes people uncomfortable and start to deeply question, well, is dark energy real? Because none of our particle physics models requires it or can explain it. Is this an error in our measurements? Do type 1a supernova, which we use to calibrate distant galaxies, are they actually all the same actual luminosity, or do they come in a variety of changing luminosities over the history of the universe that causes us to measure a false acceleration? Or is there something else going on that we can't even imagine? So when we see it, it raises all of these questions. And then we're now in an era where we can also start to measure the expansion rate of the universe kind of from first principles,
Mm-hmm.
where we look out at the cosmic microwave background and we go, okay, we know what was required to get to the cosmic microwave background. Check, we see it. We now measure the lumps and bumps in it, the hotter places and the colder places that reflect uh, the sound waves moving through the early universe. And we measure those, we get at the geometry of the universe. And then we look at when we see various structures starting to appear. And we build what's called a lambda cold dark model, a cold dark matter model of the universe, where lambda is our dark energy component. We assume a temperature gradient to dark matter that allowed galaxies to form when we see galaxies forming, that allowed clusters to form when we see clusters forming. We measure some other parameters of the universe. And all of this can be put together to get us at a Hubble value. And it doesn't quite match.
Yeah.
It's more like 72. And 72 and 68 are not the same number.
Right.
But everything matched until recently within error bars. It's only now that we're starting to get really good, tiny error bars that we have hit this problem. You can go back to past episodes of this show, and I very firmly stated the age of the universe is 16.8 plus or minus 0.2 billion. No, we don't know. We don't know the age of the
Right.
universe right now.
Yeah, it was like 13.77. Like it was getting really accurate.
Yeah.
We were for a while there it was 13.7. We were rounding it up, and then it got a little more accurate thanks to I think Planck, and
Planck.
so we upgraded it to 13.8, and now the error bars have widened again, and we're having to go 14-ish.
Well, and it's not really the error bars in our measurements that are problematic. And that's the frustrating part.
Right.
It's somewhere we don't understand something fundamental, which is disturbing. As near as anyone can tell, all of our measurements of the expansion of the universe based on what we can see and measure the distance to, those are all fine. So we think we finally nailed the parallax measurements, got the distances to Cepheids, have confirmed with other kinds of objects. We've measured the distances to nearby galaxies with Cepheids. We've compared it using red variables, planetary nebula, all these other methods we've come up with to measure distances with more or less error built in, all match nicely. We've extended out using supernova, calibrating them wherever we can with all these other distance measurements. Everything seems to work. And then we compare these measurements to early universe measurements based on cosmic microwave background and formation rates and expansion of the universe. Well, that's what you're calculating is the expansion of the universe, and that number doesn't match.
Right.
And so the question starts to become, is the universe maybe a mix of temperatures early on? Is there a mix of cold and warm dark matter? Was it fuzzy, is the way it was put in a recent paper.
That's brand new, isn't it?
Yeah. And there's questions about is dark matter changing? Is dark energy changing over time? More likely it would be dark energy is the variable culprit, but we don't know what the heck it is. So saying anything really you can't do. So we're at this point of, we know there's something fundamentally different about the universe than what we thought.
Mm-hmm. So let's in the few minutes that we have left, let's explore some of those possibilities to try to understand at least a little bit where this could be coming from. So let's start with I guess the expansion rate changing over time in a way that astronomers weren't predicting. So how would that be causing, what could that look like?
So the expansion rate changing over time currently seems to be driven by every cubic meter of universe has a couple protons of energy within it. And as near as we can tell, within recent times, that amount of energy per cubic meter has stayed constant. And so as the universe expands, you end up with more and more of this dark energy in the universe. Don't ask. We don't know. We can't explain. But this was what seems to be observed. Now, there are hints that may or may not prove real, that at different times in the universe, that energy per cubic meter may have changed, in which case you would have ended up with driving factors that affected the expansion at different rates. And we know the expansion rate couldn't have always been constant because there was an epic of inflation that got us from nothing to solar system sized in the first few moments after the Big Bang. Inflation is a thing that appears to be necessary to our understanding of the universe. So it isn't unheard of to imagine that the universe has a variable expansion rate.
Right.
It's just not something we can explain.
So I'm just sort of imagining, before we imagined that the universe, started out from the Big Bang and then it expanded. Everything got farther away from each other at some set rate that was
Yes.
slowing down thanks to the gravity of all these things pulling them together. And it should be a fairly straightforward, although very complicated measurement to make. 1998, that throws in dark energy. So, okay, so now you've got this accelerating process. So the universe has got its foot on the accelerator, and so things aren't slowing down. In fact, they're speeding up, but do some calculus, you should be able to measure that acceleration rate. But it could be that it's variable, that in fact there's
Yes.
something early on with dark energy that maybe made it expand more quickly and then it slowed down and then it sped up later on. And so if you've got that one measurement early on and you go this other measurement now and they're both accurate and they don't agree, then the universe did something weird in between the times that you were able to make those measurements from the beginning of the universe to today.
So basically, dark energy could really screw us up. And the other thing that could really screw us up is dark matter.
Right. And
Because
that was the other thing that you said, right? The temperature,
yeah,
so can you just explain what is that? Like cold dark matter, warm dark matter? Why does that matter?
it, it's a matter of the temperature determines how rapidly particles are moving. And if particles are moving too quickly, they're not going to settle down into politely collapsing blobs that form stars and galaxies. So if you have a universe that starts out filled with hot, dark matter, it's not going to form these beautiful halos that are necessary to collect in the material that formed the first stars, galaxies, and clusters. Now, if instead you have extraordinarily too cold dark matter, it will collapse too fast. So you have to have dark matter that's just the right temperature distribution, which we still judge as cold. And based on that cold dark matter, we're able to get the controlled early collapse of material into halos and structures that can explain the universe as we see it.
Now, we've got a sort of a second episode that we're going to be covering shortly. I guess for the people who are listening to this as a podcast, it comes in a week. And it's very connected and it's very related. And so if it feels like we haven't fully looked at this problem from every degree, that's okay. We're going to spend another episode going over it from a different perspective as well. So don't worry. Next week, this story continues. Pamela, before we go, do you have some names to read out?
I do. I would like to thank our patrons on patreon.com/astronomycast. Without you, we couldn't do any of the things we do. Thank you so much. We know that basically 1 in 10 of you out there donate to the show. And
Or one in
we
a
hope that more.
thousand?
Oh, you're right. You're right.
Yeah.
Dang it. I can't math.
Yeah.
Yeah, 1 in 1,000 of you donate.
Which is
And
cool. I mean, that's like
that's
that
amazing.
allows for every 1 in 1,000 of you who donate to this show, you allow that other 1,000 people to get an education in astronomy from a PhD astrophysicist for free. So thank you.
And the least we can do is say thank you. And I wish we could do more. But for now, I'm going to say thank you by name. So thank you to Jessica Feltz, Arthur Latz Hall, Tyrone Fong, Brandon Wolverton, J. Alex Anderson, Joshua Pearson, Omar Del Riviero, William Lauer, Jack, Jeremy Kerwin, Brian Kilby, Brent Krenop, Joe Wilkinson, Mark Stephen Raznak, Dustin A. Ralph, Kevin Nitka, Chad Colopy, Claudia Mastrolani, and Neuter Dude. Thank you so much for everything you do. And I wish I could say it to your face someday.
All right. Thanks, Pamela. We'll see you next week.
Bye-bye. Okay, and now we save.
So that's 541.
Okay.
And we got all the questions, everybody, but we will tackle that in the next show. So we'll just save this, export it safely, and then we will talk about what happens next.
Yep.
All right. Because you're going to have to do a thing. It's going to get a little weird.
Sorry, everyone.
Oh, no, that was a mistake. Sorry. Okay. Try that again. Okay. So I'll close that. I'm ready. Okay, so here's what's going to happen. We're going to shut down this broadcast, and we are going to start up the next one, which is going to be episode 542. So Susie just posted into the YouTube chat. So just make sure that you go to that place. I'm going to shut this stream down, take a second to get the next one rolling, and then we will start back up. So we'll see you over there in a second. All right. Thanks, everyone. See you in a second.